Hello and welcome to the continuation of unit hydrographs for ce5361. I wasn't holding out on you all, just I didn't quite get to this uh, presentation till today, so there'll be two parts to this, and this will complete an examination of unit hydrographs and how to essentially complete the homework assignment. So at this point we have read in chronological order all these various sources, and one in particular is Instantaneous Unit Hydrographs by, well, that's a terrible screen. I wonder why that's so buggered up. This particular article, I gotta find out why it's doing that. No, it must be, it's asking for money. Money has been transferred, and so now it makes all the Pictionary work. The key thing out of this article that's of importance to us is the structure of a unit hydrograph function, either as explicitly presented here on the screen or some variation thereof. And the key features we see out of that is that the kernel function as a function, see if I can get it where I can have these side by side without losing resolution. Oh, it's gone into spinning mode, which is this fancy way of saying it's going to cost me money. So our unit hydrograph generally has Q of t. Now this is the direct runoff hydrograph, and we've completely blown off base flow separation at this point, but if our time is on the left-right axis and discharge at a gauge is on the up-down axis, Q of t is some function that looks like that. And in our unit hydrograph theory, it's equal to integral from 0 to time t. Now this t and this t are the same t, usually a green t, but sometimes a herbal t. And then we have our input function, which would be our rainfall intensity or rainfall incremental depth. And let me get the times right. Yeah, that happens at time t times our kernel function, which is u of t minus tau, and we integrate with respect to tau, and there's this weight up front. So one of the parts of the weight is the watershed area, and in other weighting terms, I'll just generically call them W. So this part is what scales to a particular watershed. And in this context, watershed is everything that drains past a particular gauging station. This is the hydrograph. And this is the kernel or the unit function. I'm using the word kernel because mathematically that's what it would be expressed as, but we call it unit hydrographs as part of our engineering job security. Okay, so let's get back to what our kernel function looks like. The kernel function has an argument t, which generally refers to time, and you notice in the prior explanation it was t minus tau. That's a time shifting step, and the version that I like is something like u of t is equal to, if we use the a Boltzmann model a la Lienhardt, something like 2 over t bar 1 over gamma sub n T over T bar quantity to the 2n minus 1 e to the minus T over T bar. In the case of Leonhardt's expression, this thing is squared. We're going to depart from this because this is created under a fairly, restrictive isn't the right word, fairly idealized theory, but ours would be something like 1 over T bar. We'll stick with gamma because I'm lazy. T over T bar to the 2n minus 1 and e to the minus T over T bar raised to some power. So call that beta, probably using bad exponent choices. Well, you'll see when we get to actually doing the scripting. Some exponent. And so what this function has is clearly there's some part that multiplies time, so it has some metric of time, times some scale, that's this gamma sub n, times a decaying exponential raised to some power. So think of what you know about what the function would look like. If the exponential term wasn't there, the unit hydrograph with respect to time would have some slope to it, but we have this centering term with the exponential function, so instead it starts to look like a distribution, and this distance in the distribution space is controlled by our T bar, characteristic time of the watershed response. That was me just prettying up the diagram. And how wide this thing is controlled by the exponent. What did I call that? This exponent here. That's proportional to that exponent right there. How high it goes in this direction is controlled a large part by the value of capital N in the scaling term, and so forth. So we have three parameters. We have a characteristic time, a characteristic exponent for the decaying portion of the model, and a characteristic reservoir number for the scaling portion of the model. And in practice, you can move some of the more constants out of the integral and put them up front in that weighting term, or you can pull the weights in the area into the integral. Either one is, mathematically, it's the same. So let's return to our problem at hand, which is how to do this without invoking an easy button. Okay, so what I'm hoping you'll summarize in the essay part of the homework is that unit hydrographs can be represented in some functional form that'll have a decaying exponential part and something to do with scaling and time shifting or time centering. Let's look at our second problem. So problem 2, we're told about a watershed in Dallas, Texas. We have some pretty pictures here. The white dot in each of the pictures is identifying the gauge. If you're extra special, you can go to the latitude and longitude and convince yourself that indeed those are appropriate gauging stations. For grins, I'm going to do it because I wonder what will happen. So this is Google. Oh, I have Google Earth on this computer. I could actually do it that way. Let's do that. Let's go Google Earthing, because everybody loves to Google their Earth, right? First I gotta find it. This is hard without you all out in the audience yelling at me. It's up there to your left. Okay, do it the hard way. Googleearth. Seriously, you decide you're not going to be able to find it? Well, it should be in applications. A, B, C, D, E, F. See, I see Google Earth and the search engine can't. Classic computer. That's how they're going to get us to kill ourselves. Okay, so here's Google Earth. It's loading up on the guitar, and it probably needs, it wants some money. I wonder what happens if I deny it. Google Earth wants to use confirmation. That'd be a definite hard no. Denied. Press the close A because I don't know what it's telling me. And we'll go back to our homework assignment. Should be able to parse that all by itself, no help. So do the copy, Google Earth it, hit paste, see what happens. Of course you couldn't understand the location. You're trying to be a computer, not a human. Okay, 32 degrees. Okay, 32 degrees, 51 minutes is almost 33 degrees, so we'll do 32.9. North, 96.50 is going to be 96.85. So that, what I just did right there is called arithmetic, converting minutes into decimal, degrees into decimal degrees. Hopefully you can handle that. This thing is stupider than dirt. Yeah, now I can understand it. It looks like it's the right place. And got us awful close to we're going to have to go find the gauge. It looks to me like this is Joe's Creek. And so our gauge is probably, yeah, here's the creek running down here. You should see my little hand on the video running down there. Let's go look at the narrative description because we don't get a whole lot from Google Earth right here, except that it does go to the correct piece of the planet. Okay, what part of scroll down did you fail to understand? There you go. So it's just before the creek heads west. So in the data file itself, it tells us it's Bachman Branch at Dallas, Texas. Well, that was Joe's Creek. So we'll go back here. Bachman Branch. See if we can find that. Okay, that is certainly a more realistic location. It's on the correct creek. We'll zoom in some more and we'll see if it looks like there would be a gauging station there. We probably won't see it on Google Earth. But there is some kind of structure here. that is impeding flow, so that would be a good place to put a gauging station. It looks like a bridge of some kind that somebody's taking saw cuts to. I don't know this part of Dallas very well. Anyway, this is our aerial location. It seems to be locating correctly, and if we have the interpretation right, it should be turning to the west, probably down here somewhere. And maybe that the gauging station is located after the turn to the west. Hard to see. So anyway, going back here, we do want that aerial imagery because we have to ask ourselves about curve numbers and stuff. So delineate the watershed using the maps above as the guide, or go to Google Earth, get the location, drop it into QGIS, and perform the watershed delineation exercise as per earlier. Either one is acceptable. Actually, the only reason for doing the watershed is to verify the total drainage area, although we're going to trust the data files are correct. Then use Google Earth and determine a curve number for the watershed. Let's see if I can get found again. There we go. There's Bachman Branch. So there's our watershed, and how you would come up with a curve number. You could go to Web Soil Survey, but you have to account for fairly dense urban development. Not super dense. This looks like wealthy part of Dallas, but you can't tell from aerial imagery. Unless there's burning out car hulks, you're probably in a good part of the city anyway. I'm going to declare that a curve number is 78 because I'm super lazy, but for your homework, whatever number you come up with, be able to justify it more than I'm going to declare it 78. So curve number 7, I'm writing it down, it's off camera. Okay. Now it tells us to get the data from this data file. I'm going to see what happens when I click on it. So I'm on the development server, so I'm not sure if it can actually run me back to the data file or not. Okay, it does. And so here's what our data file for this particular station looks like. It's a rain gauge. The station number is 080-55700, and it's for a date 1966 and a storm on June 17th of that year. Our latitude is given, our site number is given. Its narrative is Bachman Branch at Dallas. Latitude, longitude, drainage area in square miles. And then it gives us some information about the contents of the data file. And the key thing is there's a column called hours passed and a column called accumulated weighted precip, and those are the two that we want to work with. So once you've determined that, you have to read that file, isolate those two columns. A key thing to note, see if I can get back to that. Oh rats, I closed it, didn't I? No, I didn't. Key thing to note is some of these data are 5 minutes apart. Some of them are 15 minutes apart. And I think some are, we're back to 5 minutes apart. So this is anywhere from 5 to 15 minutes. The times are not uniformly spaced. And that will be an issue when we try to do plotting in any sort of unit hydrograph analysis. We also are given a runoff file for that same storm event, and date and time, hours passed, and accumulated runoff. The header is very similar, and we're concerned with the hours passed column and the accumulated runoff column. The incremental runoff is in cubic feet per second. Accumulated runoff has been converted to watershed inches. So what likely is done is the instantaneous runoff between two time periods is averaged, and then the distance in time is computed. So for example, this first one's 4 to 3.4 over a 5-hour period. Then that runoff multiplied by that time duration becomes a volume. That volume is divided by the watershed area, units adjusted to be into units of watershed inches, and that's what's reported. Even modern software doesn't necessarily convert that for you. So that's an important thing to check in a practical hydrology case, is that the units don't have to be the same, but at some point when you're doing the unit hydrograph analysis or synthesis, they have to be consistent. Okay, so there's the two files, and I've already loaded it onto my computer. Again, if you are constrained to simply doing Excel versions of this, I pity you, because getting it into uniform time steps a little bit more work. You'll add rows and you'll provide intermediate times to get everything at the same time. But if you can do scripting, so either R or Python, as I have written here. If you're not familiar with Python, you can convert this into an R script quite easily, because they're essentially the same language, just different dialects. One of them is, the Central Texan version of R, the other one's the West Texan. So here's our precipitation read. We're going to read that rainfall file. I've chosen, we're going to skip any line that contains the comment marker and any line that contains capital D, so that'll rip off the header. And I have column 3 was my identified rainfall column, which is not correct. So let's go back to our rain gauge. It should be, that should be column 0, column 1, 2, 3, 4, 5, 6, 7, 8. Looks like it's the 8th column that I need to accumulate. And we can check that. So we read that, and then we're going to convert part of it into floating points. I think this should be an 8. And again, we'll read the runoff file. As before, skip the comments, skip the date time row, and then convert the column marker 1 is actually the second column, 3 is the 4th column, and let's see if that's got the 1, 2, yeah. So that should be the 3rd column. You could get fancy and have it report back the headings. And let's go ahead and have it tell us what happens after it makes that read. So here's the first part of, this is using Google Earth or something, get an equivalent for the watershed. So I came up with 78. Plot the cumulative precip and cumulative runoff versus time. Use blue for precip and red for runoff. So first thing to plot that, we have to read the data. And I think I'm printing out time for precip and depth for precip. And so it should go 0, 0, 0.1, 0, 0, 0.1. So that's working correctly. So let me shut those down. And it looks like I wanted to do the same check for the discharge. So 0, 0015, 0, 003. Let's go back up and look at the file. 0, 0015, 0, 003. So it's looks like it has read that correctly, except it got pissed at me and gave me a pink block of failure. And let me see why that is. Okay. because that should be a Q. Yay, the pink screen of failure is gone. Excellent. So there's our rainfall and runoff data series. Let me go ahead and suppress this output. Okay. Next we need to do some plotting. So I've chosen to use the plot routines that are part of the matplot library in Python plot. If you're doing it in R script, you would use the built-in plotting features. You plot one list and then you use lines to lay the other list on top. So I have it set up that list 1 versus list 2, so you can think of this as x1 and y1. List 3 versus list 4 is x2 and y2. And then there's plot titles, labels, etc. So this is just a predefined function. That's called forward defining or prototyping the function. And then we'll do the actual plot. So I'm going to set my x label as hours, my y label is cumulative depth in inches. The legend 1 is runoff, legend 2 is precipitation. Let's see if that makes sense. Yeah, because the first one's coming in as red. And then for that we put in the time of Q, the depth of Q, time of P, depth of P, and let it run. And then we've gone ahead and inserted a title. And there is our first graph. And the good features we see is that the runoff is contained entirely within the total depth of precipitation, which makes sense because it should be. We shouldn't have more runoff than precipitation in a watershed inches sense. But the other thing we see is that the precipitation signal stops somewhere here around hour 9, and our runoff signal goes on quite a bit longer. And for our unit hydrograph analysis, aka predicting future storms or doing synthesis, it would be of great interest to have these two have the same time base. So literally we need to extend the horizontal line from this last entry all the way so they end at the same time. Scripting wise, there's got to be innumerable ways to do that. I chose to just find the biggest time out of each series and then append to each series one more time increment, which is just an hour longer, and then plot it again. So now our 2 time series have the same length. Next we're going to do some arithmetic. So one thing we will find useful in arithmetic is the ability to determine the slope between 2 xy coordinates. So that's all this function here that I have highlighted does. The second thing we're going to find useful is the ability to disaggregate a cumulative vector. So you take 2 points and compute the slope between those two and report that as the disaggregation result, and then you do that for every member of the series. And we're going to need the ability to numerically integrate, which I call aggregating, and so you take 2 adjacent points, add them together, and carry a running sum. So you can look at those at your own. So this one does incremental to cumulative, this one does cumulative to incremental, and that one just gets slope. So we're going to get the incremental rain and the incremental flow from these. Essentially we'll be differencing each of those points and getting an incremental result for each of them. And we're going to use the disaggregate function on the precipitation depth and precipitation time, and the disaggregate function on flow depth and flow time, and then report back the results and plot them. So there's our two time series, and these are now reporting in inches per increment, so it should be inches per, these are hours, so these will be inches per hour. And now things start to look a little bit different. Instead of being cumulative, we have these two spikes of rainfall, no surprise there, and we have two corresponding spikes of runoff that roughly looks like an attenuated rainfall, time shifted about 7.5 hours. So if you can visualize the red curve being shifted to the left 7 hours, that hump would be about there, and this hump would be about here. There's a fair amount of attenuation in these two signals, because remember they've been scaled into the same depth units. We'll find it a lot more useful to interpolate everything into whole hour time increments or whole minute. Here's an interpolation program. It uses a function in the SciPy package, but you could just as well write something like this on your own. So it takes a pair of x values, it takes a collection of x and y values, those are our input time series, and then produces new x values, and an input of new x values where we want it to put the results, and then it will compute the associated y values with the new x values. So we're going to, for the flow, we're going to put the original time for flow, the original incremental for flow, and then we're going to have this time of the model. And the time of model is going to be every hour starting from 0, ending at big time plus 1, so 25, 0 to 25 hours. There'll be 26 entries in T model, and then for the precipitation, we take the time of the precip, the incremental rain, and then the time of the model. So we're going to map these real observations onto these uniform times of interest, and then we'll go ahead and plot the result. So there's what our inputs look like remapped onto hourly. You should observe immediately that we're losing information because we're losing these small scale changes here and here when we do that. It turns out, from my experience, this works better if we go to relatively short times. So let's modify it, and we'll do 1 minute. Now remember, this is all modeled results from original data. So you can argue it's still data, but it's just a reinterpretation of it. So now we're going to put everything into inches per minute. And all we did to do that was just change the T model range and then convert the actual times into minutes. And there's our two events interpolated onto 1 minute time intervals. And so that picture clearly looks like that, as it should. That's the intent. And now we can try to represent the red curve based on a kernel function in the input from the blue curve. So here's our kernel function. It looks like I have some scale constant, 2n minus 1 t bar and an n2. The n2 is the one that I was mentioning. Let's see, that's k3 that goes onto the decaying exponential. K2 is a mountain in Nepal. It's also our resonance time parameter. So K2 is very important. K1 is just a shape parameter. Has a notation here. It should be integer. Should be integer. That's for theoretical purposes. I'm pretty sure we can use floating points and this will run. Next thing is we need to have a convolver that performs the convolution integral. So the convolve function essentially does it performs the discrete integration of that thing. So what you supply to the convolver are times, the input time series up to that time, and the path to the kernel function. And let's take a look at this. So this is expecting the excitation list, and we have to pre-compute the kernel responses, which is easy enough. That's why it's called a unit hydrograph. So N1 is the length of the kernel, already has to be populated. Excitation is the list of inputs. Kernel is a list of responses. The response is the convolved response. So this is our convolver. It's kind of interesting to think that such a funny looking integral degenerates to 6 lines of code. Our next step is we have to apply whatever loss model we're going to apply. For the sake of this quick demo, I'm just going to use proportional loss, but we'll go back and, using the curve number of 78, try to figure out what the rainfall would look like in that situation, and that gets applied to this excess rain list. So this part right here, that's the loss model. Whatever loss model you do, you would have to tell it whether rain can become runoff or not. And now we'll actually build the unit hydrograph. So we need to know the length of the excess rain function. We'll go ahead and set the kernel storage to just an empty list. Preset parameters for our unit hydrograph, and then go ahead and populate the kernel function, populate the kernel with the kernel function parameterized by these parameters, populate the response using the convolver, and then we'll plot everything. So in this case, because we're constrained to blue and red, because I didn't want to change the plotting algorithm, the red trace is the observed hydrograph at the gauging station. The blue trace is our unit hydrograph model for the same rainfall that generated the red curve. And clearly there's been some curve fitting going on here to make them line up that good, because you wouldn't know that ahead of time. And if you chose naive time shifts, it looks to me like that's almost 500 minutes to get from the peak of that to the peak of that. Maybe less. Let's call it 400 minutes. So your initial guess might be 400 minutes. No clue on shape, so my initial guess for shape might be 3. So 3 minus 1 is 2, and 2 factorial is 2, so my initial guess of scale constant would be something like 3. And K0 is going to, our initial who's and what's it would be 2. So that would be honoring the unit hydrograph that's in the paper. If we did that and rerun it, that's a terrible model of the observed data, but the key feature is at least they're plotting on the same axis. And then from here we could start to play games. So first thing, this one's centering here, and this one's centering here, so it seems like the time shift is too big. We'll leave time shifting alone for the time being, but the decay isn't fast enough, so we might increase our decay rate, rerun the model, and that's better. Now we see that the time shifting's off. We might increase our decay rate even more. We might regret that one. I'm going to go with that. All I'll do is break stuff. And we're pretty close on the peaks, and then we could mess with the scale to try to get that peak to match. But let's work on our timing parameter. And when you change time, everything else is going to start to change again. introduce my scale constant. I'll make it a little bit bigger and see what happens. Probably should have saved it. So that scale constant's too big. So go back to 2. I think 2 was what I had. That one's too small, but I'm going to mess with the shape parameter a little bit. I think I want this to be a little bit bigger. Now I have a lot of experience with messing with these, so that's why I'm arbitrarily, okay, make that 6, that'd be 7. And where's my model? There it is. God, what part of input did you fail to accept? Try to get back to whatever I had before, because that was a good model last time. I forget if the shape needs to go up or... I'm going to stop there for the time being. And so let's stipulate. We fuss around for a while, and that's the best we can do. Now the obvious thing is this trial and error part can be fairly easily automated simply by calculating the square error between the blue and the red and instructing the computer to automatically make changes and best fit the model. So a quick check on whether our model is usable or not would be to plot the rainfall and runoff results. And so we input hydrograph in blue, output hydrograph in red, observed. Input hydrograph in blue, model hydrograph output in red. And clearly the model one is smooth compared to the observed. That's anticipated. But we could argue that that's a pretty good fit. So we have found a unit hydrograph for our model. And in our case, actually I want to do I'm going to try to make it a little bit prettier. Okay, that's peaking about the right time, and this needs to go up. I'm going to go with that. So we're introducing early runoff that is not observed in the real data, and we're decaying a little fast on the backside. Again, we're just pulling functions out of the air at this point. So we could declare our unit hydrograph for Bachman branch as unit hydrograph as a function of time is equal to K0, whatever that is, over gamma of K1 plus 1 over 2. Two divided by K2 times time over K2 this is raised to the K1 power and then times exp of time over K2 should be the K, I think that could be the K3 power. K3 power. And we could actually stop there. So K2 is our residence time, so if we make a quick modification, gamma k1 plus 1 over 2, 2 over t bar, t over t bar, raised to the k2 power, e to the minus t over t bar, raised to the k3 power. That's the unit hydrograph that this particular computer program is representing. You didn't see me write any of that. There it is. So that's our unit graph function. Now, if we search the literature, this is close to a theoretical unit hydrograph based on the Boltzmann molecular speed distribution with the modifications that K3 is no longer constrained to be low integer, and I made a little bit of flexibility with the K1 plus 1 term. This has a few more degrees of freedom than a formal one might have. The point being, unit hydrographs is just postulating a function for the kernel, fitting that function to the observed data, and now in our case our unit hydrograph is, and write down our numbers. (7.5) over gamma. Now let's see, k1 plus 1. 5 plus 1 is 6 over 2, so that's 3. 2 over 470 in minutes. T over 470. K2. Oh, that can't be to the K2. No wonder that thing isn't. Yeah, it's to the K1 power. E to the minus T over 470. And our K3 is 2K0, so 4 is 15. Okay, so there's what my function written out would look like. And again, doing it in scripting, it's all stored within the script. Okay, that is the analysis part. Now, in practice, you'd want to use more than one storm if you have sufficient data. And you probably want to examine the values of the various exponents and constants to convince yourself that you have some tie back to reality. So me using the real high decay rate on the exponential is disturbing to me, but we'll save that for later to deal with that disturbance. Our third problem is now to apply the unit hydrograph. Good, looks like I've not done it yet. I will say that for a subsequent video. This one's real long. So I'm going to stop recording, upload this, and I will continue with part 3 of the exercise shortly.